Okay, so the problem that we're going to be dealing with here is a freefall problem, and it has to do with finding the maximum height that a stone can be thrown on the surface of the moon, given that it can be thrown a certain distance on the surface of the Earth. So the problem reads: the acceleration due to gravity at the surface of the moon is 1.67 meters per second squared. If a person can throw a stone 12 meters straight upward on the Earth, how high should the person be able to throw a stone on the moon? Assume that the throwing speeds are the same in the two cases. Okay, so what we're going to be doing is trying to find the maximum height that the stone can travel on the moon, and this actually means we have to consider two formulas here. The first one is the distance formula, right? The constant acceleration formula for distance, and the other one is the final velocity formula. Okay, so let me write that down. The first formula, we have y equals v0t minus 1 half gt squared. And the second formula is the final velocity formula. V sub f is equal to v sub naught minus gt. Okay? So the thing is, if we want to find the maximum height that the stone can travel on the moon, then we're gonna have to solve this formula, right? This is the height formula. The only thing is we're not given the time of travel of the stone. Okay, so this is where the final velocity formula comes in. We consider that when the stone reaches the maximum height, its final velocity is equal to 0. Okay, so let me write that here. At maximum height, v sub f equals 0, right? When you throw something upwards, when it reaches the maximum height that it can travel, it stops momentarily before falling back down. So we can write this as 0 is equal to v sub naught minus gt, which means we can solve for t. So we find that t is equal to v sub naught over g. Okay? So let's box this off. So we can substitute this value of t, right? We don't know what exactly it is, but we have it in terms of the initial velocity and the gravitational acceleration, which is good. So we can substitute this value into this equation right here, right? So that our maximum height formula is solely going to be in terms of the initial velocity and the acceleration due to gravity. Okay, so with that we can write, let's choose a good color here, y is equal to v0 multiplied by t, but t is equal to v0 over g. So y equals v0 multiplied by v0 over g minus 1 half g v0 over g squared. Okay? If I distribute the v0 in here, I find that this is going to be v0 squared divided by g minus 1 half. Now here you're going to have a g squared in the denominator. So g cancels out with one of the g's in the denominator and gives you a v0 squared over g. Okay? So v0 squared over g minus 1 half of v0 squared over g gives you a half of v0 squared over g. So we get v0 squared divided by 2g. Okay? So here we find that our maximum height formula, we can write that as y max is equal to v0 squared divided by 2g. Okay? So notice how general this formula is, right? It's not speaking only in terms of whether you're on the moon or you're on the earth. It doesn't really matter. It's telling you that the maximum height that you can throw an object is equal to the square of the initial velocity with which you throw the object divided by twice the gravitational acceleration of the planet you're standing on. Okay, so if we're on Earth, then G would be 9.81. If we're on the moon, then G is going to be 1.67. Okay, so this means we have two cases now. Okay, so case one is going to be Earth. So for case one, we know that the maximum height is 12 meters, right? A person throws a stone 12 meters straight upward on the Earth. So 12 meters is equal to V0 squared divided by 2 times G. But see, on the Earth, G is 9.8. So we can say V0 squared divided by 2 times G on the Earth. Okay? That's why I put the subscript E to say this G is for the gravitational acceleration of the Earth. Okay, so case two, we're on the moon. And on the moon, we don't know what the maximum height is. So we'll just put it as Y max. So Y max is going to be equal to, again, V0 squared, right? But this time divided by twice the gravitational acceleration of the moon. So that's going to be 2G of the moon. Okay? So you see here that if we can solve for V0, we can plug it in here and solve for Y max on the moon. So let's go ahead and do that. We find that V0 squared, if we consider the first case, we find that V0 squared is equal to 24 times the gravitational acceleration of the Earth, right? G sub E. So we can plug this V0 squared into here for the second case. Okay. So if we consider the second case here, then we can write Y max is equal to V0 squared over 2GM, right? Where V0 squared is just 24G of the Earth. So 24G of the Earth divided by 2 times the gravity of the moon. Okay? 24 over 2 gives you 12. So Y max is equal to 12 multiplied by the gravity of the Earth divided by the gravity of the moon. Okay, and that's going to be 12 times 9.81 divided by 1.67 meters. And if we put that in the calculator, that should give us roughly 70.5 meters. So on the moon, the maximum height that you can throw the stone, given that you throw it with an initial velocity of this much, then the maximum height that the stone can reach is 70.5 meters.